Welcome to this tutorial for students studying Mathematical Methods, Unit 3 in Queensland. In this session, we'll be covering questions on differential and integral calculus, exponential, logarithmic functions, including applications of these. The questions have been selected to highlight a range of ways that you can use the TI-84Plus CE to explore, calculate, and verify answers in typical exam-type questions. If you're watching this on YouTube, then you can download the question sheet using the links below and post questions in the comment section. So let's get started. Our first question, it's a musical question. You don't get to hear anything, but the average person can hear frequencies ranging from 30 Hertz through to 18 kilohertz, meaning 18,000. Middle C is defined as 262 Hertz. Each octave higher represents a doubling of this frequency, and each octave lower, a halving. So our question is, how many octaves can the average person hear? Now the question doesn't require us to have any musical knowledge as such, but I'm going to put up just an example of a piano keyboard. I've labelled some keys, and we can see middle C at 262 Hertz. So one octave up, in other words, the next C, is 524, double the previous one. So the next octaves would be 1048, 2096, and so on. In other words, a doubling of each frequency for each octave. And if we went down in the opposite direction, we'd kind of see the same thing in reverse. So in other words, 131 Hertz and so on. I'll start with the equation y equals 262 by 2 to the x. The 2 to the power of x is our exponential component, and if x equals 0, we'd see that y equals 262 Hertz, middle C. I could have used any of our other values like 524 or 131. I've just chosen to use it as 262. So let's have a look at how we do all of this on the calculator. I'll start by entering in my equation 262 times 2 to the power of x. In here, in my 2, I'm going to put 30. That was the threshold given to us as the minimum that we could hear. 18 kilohertz or 18,000 hertz was the highest frequency that we could hear. Next, I'll set up the window settings. I'll go from -10, that's 10 octaves below, and 10 octaves above. And then I've set the Y minimum, as in hearing, 0 hertz, through to 20,000 hertz in steps of 2,000. So let's have a look at the graph. The blue graph is our exponential function, that is the scales, and the red one, which looks as though it's almost on the x-axis because it's so close, is our 30 Hertz, and the black one is the 18,000 Hertz. So I can use the calculate feature to calculate where the graphs intersect. So I'll choose the first curve as my sound, and in the second curve is my lower frequency. And I'm not going to bother with moving it to get the guess. I'm just going to leave it where it was because the calculator will find it. And it says -3. That means we can go down 3 octaves, or here, 3 octaves below middle C. So how far above middle C can we hear? I'll do the same thing. We'll calculate the point of intersection, option number 5, and our first curve is our 262. We can see it's written at the top of the screen. And this time I want to choose the other curve as my 18 kilohertz or 18,000. Press enter, and I'll give it a bit of a clue. I'll say it's over here somewhere. Again, I don't need to be too accurate. It's only crossing at one spot, and I see the result is 6.1. So I can hear 6 and a bit octaves above middle C. I can hear 3 below, 6 above. So my answer to this question is that I can use 9 octaves altogether. Now, I could have used the numerical solver to do this question as well, but I've just chosen to do it graphically. We'll jump into the numerical solver in a couple of our other questions. So let's have a look at question number 2. Question number 2 says, determine the exact value of this horrible expression here. Looks a little bit scary. The first thing I can notice is that all the bases are different. So I'll start by having a look at how we might solve this on the calculator. You may not be aware, but you can actually create a different base on the calculator. So let's go back. I'll go back to my home screen, and I'll start just to demonstrate how we do the log of a different base. If I do log and I don't specify the base, it will default to 10. The first part of the question said log of 3 with a base of 2. So what that means is 2 to the power of that thing there, the 1.58, is equal to 3. That's what log base 2 of 3 means. Now I've got to calculate log base 2 of 3 multiplied by log 4 base 3 and all the way up. That's a lot. But I can generate all of those bases because it would take far too long to do it by hand. I can generate all of those bases very quickly in a list. So I'll go second list, across to operations and down to sequence, option number 5. I've got my expression x, variable x. I'll start at 2 and end at 63 with a step size of 1. And I'm going to store all of those values in list 1. So you can see these are going to be my bases, 2, 3, 4, 5, etc., all the way up to 63. So what I really need to do is the same as what I did in the first line. So I'll do the log, and the values I want to calculate the log of start at 3, so 1 more than what my list is. And the bases are all stored in list 1. So what that's going to do is log 3 base 2, log 4 base 3, and so on. I'll press enter, and it's generated them. You can see, just as verification, that the first answer, 1.5849, is the same as what I had before, so all is looking good. I really need to keep a record of all of those, so I'm going to store those in list 2. Now the question asks me to multiply all those values together. Again, you wouldn't want to go in and do that by hand. That's 63 numbers you've got to enter in or thereabouts. So let's have a look what other features we have that we can do with lists. It's not an operation, it's actually some mathematical stuff that we're doing. We're not summing them, we're finding the product. So option number 6, the product of all the values in list 2. And that might be somewhat surprising. I get 6, an integer quantity for this amount, which suggests that there must be some simple by hand approach to doing it. Nevertheless, I've got the answer to my question. But let's go back just for completeness and have a look how you might have done this if you're doing it by hand. We suggested that there was a change of base rule that was applicable. So I'm going to start by changing our first term, log base 2 of 3, using a change of base rule. Fairly simplistic. We can see the denominator, log 2 of 2, would equal 1, so it'd simplify back to what it was anyway. But let's just swap it out anyway. So now let's have a look if I change out the next term, log base 3 of 4. Again, I'm just going to use the change of base rule. And I'm sticking with a base of 2. Because I'm trying to get all the bases the same. And I can do the same to the third term. And hopefully by now you're starting to see a pattern. And I don't have to do all of these by hand, otherwise I might as well have done it on the calculator. Hopefully you're starting to see that there's some terms here that kind of simplify those ones. and the next ones, and the next ones, and so on all the way until we get to our very last one, which would be log base 2 of 64. Let's just go back to the calculator. Log base 2 of 64 is the only term that we'll have left, which is 6. Exactly the same as what we've got when we use the calculator to do it by grunt. So, again, an option to do it by hand, or if you know your way around the calculator, sneak your way to do it. Next question. This time we have to find solutions to this nasty expression. So this question could be solved on the calculator. What I'm going to do is just start the process by hand just to see that it is actually quite a complex problem to solve. You need to know your log laws. So the first thing that we'll do is transpose the equation a little bit just to put the 5 on the other side. Ultimately what I'm trying to do is put everything into logarithms. So I'll change my x plus 5 to log base 2 of 2 to the x plus 5. Now I can cancel out my logs and I get this expression here, still not looking a lot better than what I had before, but we're getting there. The trick here is to note that 4 to the power of x is the same as 2 squared to the power of x, which I can rewrite using our index laws. And then finally, recognizing that we have 2 to the x sort of on both sides, I'm going to make it look a little bit simpler by calling that a. Now it's starting to look a bit easier. Now it looks more like a quadratic. And given that we have a quadratic, we could expect 0, 1, or 2 solutions. And so we could continue with our by-hand approach to this problem. But this is a session on how to use a calculator appropriately in an exam. So let's have a look at what the examination solution might look like. To save a bit of time, I've actually stored this question on my calculator. To retrieve the question, I'm going across to what we call a graphical database. I'm going to recall option number 4, and I stored it effectively like question 3, so I stored it in graphical database number 3. I've just done this because it was quicker to do that than what it was to type the question in. So I've done the left-hand side of the equation, log 4 to the x plus 31 in base 2, subtract 5, and the right-hand side of the equation as simply x. The other beauty about that graphical database is it recalled the window settings that I used for this question. So, looks like we've got one solution, but have a look on the right-hand side of the screen. It almost appears as though the lines are parallel. We need a bit more information here, and it's one of the tips that I'll give here is that always check your window settings. Is there some information that we're missing? The by-hand solution suggested we might be looking for 2. So let's just change our window settings. I'll change the zoom. There's a few options here for us. I'm going to choose zoom standard, number 6. And indeed, we see our 2 solutions as suggested by the final step in our by-hand solution being quadratic. Now it's the same as what we did before, and that is we can calculate the point of intersection. So calculate point of intersection and first curve, second curve, and guess. And interestingly enough, our first one is at x equals 0. And if you think about what's happening there, you might be able to see why we'd get a solution when x equals 0. Now, as for our other one, how do we get the other solution when I've calculated one of them? So we'll go calculate, point of intersection, and this time we'll scroll along. Here's our first curve, second curve. We just need to make sure that our guess is a lot closer to the other solution. Otherwise, it'll just come back and find our first one. So our solution is at x equals 4.95. We can also make sense of this solution, by the way, because if I have a look back at the equation 4 to the power of x plus 31. As x increases, and 4 to the power of 5 is a fairly big number, and if I add 31 to that, it's not going to make much difference to my answer. So really what I'm left with here is the log of something, let's say 4 to the power of x, and just ignore the 31. We're going to get something pretty close. And then if you finish that off by hand, you'll see why 4 to the power of 5, and then we take log base 2 of that, comes out pretty close to what we're looking for. Slightly less at 4.95 because we've got this 31 here. So do go back and have a look at that question because there's some cool stuff happening if you want to look at limits. All right, question 4. Determine the derivative of y equals sine x, log of sine x, and state the corresponding domain. Now, we don't have a computer algebra system, so we will need to do the derivative by hand. But it's almost straight out of the QCAA book of information for your subject for mathematical methods that says when you're doing the derivative of log of some function, it's just f dashed of x on f of x. So we know that the derivative of sine x is cos x, so we should see cos x on sine x as our solution there. That's the first part. We might choose to simplify that a little bit and call it 1 on tan x. So we've done our derivative, but we haven't done anything about the domain. And here's where we can use the technology in a different way. It would be very easy to make the mistake here and look at tan x and say, oh, I can't let tan x equal 0, and therefore answer it as the domain tan x not equal to 0 and find out all the values for x. Unfortunately, that would be wrong. Let's have a look at the calculator. How can we use the calculator to check or inform us or make us think more about this question? Again, I've put the question into a graphical database just to bring the information back a lot quicker. So I'll recall, and it's question number 4, so I'll recall graphical database number 4. And there's the equation that we're given, log of sine x. And in y2, I've told it to draw the derivative of that function. Again, it's not going to give me the equation, but it will tell me what the graph looks like. I set it to go between negative 2 pi and 2 pi. And now we can see the blue graph is our log of sine x, and the red one is the derivative. It certainly seems to have a lot of gaps in it. To give us an idea on why so many gaps, let's go back and I'm going to add in a graph of sine x. So if I put sine x in here, you can see our derivative function only exists when sine x is greater than 0. So in actual fact, the solutions that I need are for sine x greater than 0. So the domain, to answer a question concerning the domain, we're focusing on our original function, that is the log of sine x, not the derivatives. There's no point finding the derivative where the original function doesn't exist. So we need sine x, the thing that's in the brackets inside that logarithm, to be greater than 0, and make sure you get that inequality correct. We can't have it equal to 0. So there's our solution, a general solution. The exam question doesn't necessarily have to be exactly the same as this. It might give you a restricted domain over which it's going to operate, and then you might have to impose more restrictions. But this gives you some idea on how to use the calculator to check your answer. I didn't come up with the derivative, just used it to have a look at what the domain might look like. Okay, next question. A tangent to the function. Pretty fancy looking function, and there's a parameter involved. is drawn at the point when x equals 1. Determine the points of intersection between the tangent and the function f. So I've got a diagram on the screen there so you can see what we're working towards. I'll probably want to extend that. It looks as though it's going to be pretty close to hitting the graph at the x-intercept on the original function. So we could start this off by hand and say, well, how am I going to do the tangent? I need the derivative of f of x. So I'm going to expand it. And we get something that kind of looks like that when you expand it out. So our derivative is relatively straightforward. There you get 3x squared minus 2cx minus 4x plus 2c minus 3. And I need to know what is the derivative when x equals 1. So I could substitute 1 and I get that, which simplifies a little bit to give me m equals negative 4. We see that the minus 2c and the plus 2c, interestingly, cancel out. So now I know the gradient of my tangent. I can write it in this form, what we call the translational form of a straight line, y equals m bracket x minus h plus k, or our k value is just f of x. So I need to know what f of 1 is in order to figure out the final part of this tangent line. So I go back to my original function, f of 1, and I get 4c minus 4. So in other words, in this tangent equation, I need to replace the f of 1 with the 4c minus 4, which simplifies to that. So that's the equation to my tangent. Now I need to find the point of intersection between my tangent and the original function. So we make those two equations equal to each other. I'll do it in expanded form because I need to expand it to start simplifying. I can see there's some c's on both sides, some x's on both sides. So if I collect everything on one side, it'll simplify a little bit. And then I can start to factorize. But now I'm thinking you're seeing that there's a lot of work in this question by hand. Surprisingly, we can do it all on the calculator, even though we have the parameter. So we can then factorize that. We see a quadratic and a linear. Quadratic comes out nice. So we see two solutions, x equals 1 or x equals c. Well, x equals 1 was kind of obvious. We drew the tangent to the curve when x equals 1. It's this other one, this at x equals c, that's interesting. We haven't finished our question yet because it did say points of intersection. So we need to substitute those values into our original equation, and we get those 2 points. The first one is where our tangent crosses the original function. The second one, c, 0. Interesting. So that suggests that the tangent crosses f of x at the same point that f of x crosses the x-axis. So let's go back to the calculator and see how we might use the calculator to answer this question. Once again, I've taken the liberty of storing my equations in a graphical database. It's only to save time in this presentation. So I'll recall we're doing question number 5, so I stored it in graphical database number 5. So there's my equation in y1, x plus 1, x minus 3x minus c, and I've done the derivative plus some other stuff. You recall in my by hand solution, I said that it's the translational form of a straight line. So the first part in my derivative of my y2 is this derivative. The derivative of my original function when x equals 1. Go back to the by hand solution and you'll see that that's our value for m. Then the translational form of our straight line or our tangent, I know it crosses the function when x equals 1, so it's x minus 1 plus y1 of 1. So that will be the tangent. So how does the TI-84 calculator handle this C? Well, it would use whatever value I've got stored in C and do that graph. I want it to be a bit more dynamic. Now, this is not necessarily what you do in an exam, but kind of cool that we can do this. It only takes a moment. So I've turned on what we call transformation graphing. So now I've graphed my function. You can see that the red graph passes through my cubic at the x-intercept, or at least it appears to. That's when C equals 4. I can change the value of C and see that it's still passing through what appears to be the x-intercept. Of course, to check that, I would do a calculate or do a substitution. But I'm at least seeing that the answer I got by hand with all the parameters seems to work. That is, our tangent at x equals 1 is always passing through the other function, our original function, where it crosses the x-axis. And I'm just clicking on the left arrow to change the value of C, and the graph has changed. It'll be interesting to see what happens when that is actually a turning point, and it still works. I wonder what happens if we manage to do it in between the other two intercepts. And we see our tangent line is now going through C equals 2, and it's crossing the x-axis at 2. So, interesting question. Now, I see some people asking about how do you do the derivative function on the calculator. I've just been doing a recall, but the easiest way to do it is if I wanted to graph the derivative of something, then I can go into Maths, and option number 8 is derivative, and it gives you the derivative template. So what I've done in this question so far is I can put x, I tell it what I want to do the derivative of. In this case, my equation is stored in y1, or you can type the equation directly, like if it was sine x, put sine x in there. To get my y1, I'll press alpha and trace, and there's y1. Now, if I want to calculate the derivative for a specific value, such as in the example above, when x equals 1, I'll put a 1 there. Or if I wanted the gradient when x equals 2, I'd put a 2 there. But if I want it for every possible value of x, then I put the x in. So now I can draw the derivative of whatever is in y1. A very cool trick. Well, it's not really a trick, it's a skill. Something that the calculator can do. So our solution seems to be correct. So in this case, I've used the TI-84 calculator to, in a sense, verify the solution that it's crossing at the point C, 0. So my by hand solution is being validated with the calculator solution. Right, next question. Now moving along quite fast, remember this is being recorded, so you'll be able to watch this later on YouTube, and that way you can pause and keep up with what we're doing. Question 6. Given the polynomial p of x equals x to the 4 minus 6x cubed minus 24x squared plus 6x minus 9, determine the range of values for x such that p of x is convex. Convex. This is just one of those things that you have to remember, is that a function is concave up or convex when the second derivative is greater than 0. And the converse, it's concave down when the second derivative is less than 0. So it's talking about the curvature, the way in which the graph is, if you like, bent or curved. And for concave up, or often referred to as convex, we can see this numerically or algebraically using calculus as the second derivative being greater than 0. Now, let's get our head around the problem. This is a power of 4, polynomial degree 4, and if I differentiate it, I'll get a polynomial degree 3. If I differentiate it again, I will get a polynomial of degree 2, so a quadratic. And I need to find out when is that quadratic greater than 0. So that's the problem that we're trying to solve. So let's have a look at a calculator-based way of doing it. This is question 6. So I'll recall the equations for question 6. So x to the power of 4 minus 6x cubed, that was the equation that we're given. You can see in y2, this is very careful, y2 says I'll calculate the derivative of whatever's in y1, and I'll do it for all values of x. In other words, I'll draw the derivative of y1. In y3, I'm calculating the derivative of whatever's in y2. But we know y2 is the derivative of y1. In other words, y3 is actually going to be the graph of the second derivative. Now at the moment, these funny little cursor things next to my y1 and y2 tell me that I've still got that application turned on. So I'm going to jump out of here, go back into transformations and switch it off. And now I can just go back in here and you'll see that these have returned back to normal. I've got the first derivative turned on, and I only want to see the second derivative because for concavity, I'm interested in the second derivative. So press graph. The blue one is my polynomial degree 4, and as expected, I've got what appears to be a quadratic for the second derivative. And I need to know when is that second derivative greater than 0. So I can't solve greater than 0, but I can solve at the boundary points, that is when it's equal to 0. So I'll go second, calculate, and I'm solving, oops, let me try that again. I'll go second, calculate, and I want to do the 0, so number 2. And I want to do that for my second derivative. So I'll put the left bound there and the right bound there and have a guess. And it takes a little bit of time because it's calculating the second derivative and trying to solve it equal to 0. And it says it's x equals 3.99999, which I'm pretty confident to say would be x equals 4. The other one appears to be that x equals -1, but we'll check it anyway. So calculate a 0 on my second derivative function, and then I need to put in my left bound, which is over here, and a right bound. It's handy that it draws those lines in, sort of indicating our solution is somewhere between the two, and guessing somewhere around about there. And indeed, x equals -1. So the solution to our question is our function is convex when x is less than -1 and when x is greater than 4. So they're our two regions. And of course, as I said, we could have done that question by hand. Part B, the question gets a little bit harder. You can see that our number, our coefficient for x squared, has been swapped with a parameter a. So as we change that value of a, obviously our polynomial degree 4 is also going to change shape. And based on the question, we'll assume that by changing it, we can make it so our original function is always convex. So if we're thinking about what's happening at a higher level here, we want the second derivative to be greater than 0. We know that our second derivative is a quadratic, so we're looking for the situation when our quadratic will always be greater than 0. That's the problem we're trying to resolve. Now, how much of that can we do on the calculator? Well, we could do this by hand. We could do the derivative and go through those steps. Let's just go back and have a look what the problem looks like on the calculator. Now, you recall as I did before, when I wanted to use a parameter, I used in the graph, I used that transformation app. One of the restrictions with the transformation app is that it only graphs the first two functions, y1 and y2. So I need to get the second derivative in here. And the first derivative down here, I don't need to see the first derivative, so in fact I don't need it graphed. So I'll change this one to the first derivative. So that's going to calculate the derivative of y1. So y2 and y3 would be exactly the same at the moment. They're both graphing the first derivative. But I want y2 to be the second derivative. In other words, the derivative of the derivative. In other words, y3. So now y2 will be the second derivative graph. And I want them interactive, that is, when I set a parameter in here, so I'm going to set this as plus a times x squared. That's what the question gave me, and it wanted to know for what values of a will this function now be convex. So I'm expecting to see polynomial degree 4. I'm expecting to see a quadratic. So what does it do for our value of a? Well, I'm going to start just by guessing 5 for our value of a. I don't know what it had before, but I'll start with a equals 5. And I need to turn the transformation app back on so I can explore the a. And now I'll graph it. It warns me that it's recognized that I've got other graphs in there. So I'll just accept that. Now with a equals 5, you can see that my polynomial degree 4 looks a little bit different than what it was before. Remembering before it was some other value, I think it was minus 24. Now that it's plus 5x squared, it looks a little bit different. You can see that my quadratic is now looking like it's almost completely above the x-axis, apart from that little region. So what happens as I change the value of a is that the original polynomial will change. It takes a moment, and then the second derivative changes. So I'll change it again, and we can see that as I increase the value of a, our parabola is moving up ever so slightly, and we can see that our polynomial degree 4 is also changing. So as I keep on going up, I'm getting closer and closer to the situation where my quadratic is almost completely above the x-axis. In other words, my original polynomial degree 4 is almost at the point where the entire curve is convex. It appears as though it's almost there now. You can see here, as we pass through, it comes down here and then seems to almost continually go upwards. So it seems to be around about that 12 or 13. If you go through and calculate the derivative, we can work with the discriminant. So there's our second derivative, 12x squared minus 36x plus 2a, and we need the discriminant of that to be negative. In other words, solving the discriminant of this quadratic so that it's always less than 0. So I could factorize it. I could put it in turning point form. So turning point form would be one way to do that because it doesn't look like a very attractive quadratic. Or I could just go back to the calculator and say, well, you know what? I can use the maths solver option, the numerical solver, And look at that. I've typed it in before. So b squared minus 4 times 12 times 2a, that's my discriminant. And I'm trying to solve that at the limiting case when it equals 0. So if I press enter and solve, it comes up with the solution, 13.5. So what it's saying is that if a equals 13.5, that entire original function will be convex. Now I'm required to find the range of values for which it's going to be convex. Based on what I saw before, I would say all the values greater than 13.5, but be careful. Let's just double check what we know about the discriminant. If I'm looking at 36 squared minus 4 times 12 times 2a, we can see as a increases, this is going to become more and more negative. In other words, the quadratic will continue to be above the x-axis. So our assumption, based on what we saw visually, is correct. And our answer is a greater than 13.5. Right, I think we have time for one more question. That's this one. It's an integral calculus problem. I think there's 2 more questions on the question sheet, but we'll only get time to finish off one of them, I think. So this one's an interesting one because there's not actually a lot you can do with the calculator to help you. It's an interesting one. But again, it's a situation where once you've got an answer, you can kind of check to see whether or not you're on the right track. So we don't even know what our original function is. It says it's just some function f of x, but we do know that its integral between 0 and 3 is equal to 12. And we're required, to determine the integral of 2 times f of x plus 1 between the same limits. My diagram on the right-hand side gives us a clue as to what's happening. That is, it could be transposed up by 1 and dilated to see this new area. So we can see the area is probably different. So it's one of those ones you'd need to do by hand. But there's a little trick that you can do. So this is question number 7. Let's see if I put the graph in question number 7. Nope, didn't put it in question number 7. But let's play around with one. And I need to turn my transformation graph off. I'm just going to do x squared. So I'm going to graph that, and I'm going to set my window dimensions -5. No, I don't even need to go as far as -5. Let's do -2. And up to 5, because the question only goes between 0 and 3. -1, let's say 12. So there's my graph. I don't know that the area is 12 between 0 and 3, but let's find out what that area is. So let's do calculate the integral, number 7, between 0 and 3. So I can see that the answer is 9 for the area. The question said it's 12, and the question didn't give me a function, it just said f of x. But that would assume that it must be true for all functions that have that area. So I can change this up a little bit. In fact, if I put 12 in here and then divide it by 9, so I'm just dilating my function a little bit. There's my graph. And if you're wondering how the graph went so quick, here's another little tip. If you're not super interested in the resolution, you'll notice if I change it and I make it 1, it actually takes a little bit longer to graph. The resolution's a little bit higher. If I change that to a 5, it graphs really quick, but not as accurate. I'll put it back to its default at 3. And I want to calculate the area, that is, number 7, between 0 and 3. And on behold, I get 12. So all I've managed to do so far is get the area that was suggested in the original question. But it says, let's go back to the original question, what would be the area under 2 lots of f of x plus 1? Let's find out. So in here, I can have 2 lots of f of x. Well, f of x, I'm going to use the variable key this time. It's a y variable, it's a function, and it's in number 1. 2 times that one plus 1. But I want to calculate the integral. I wonder if I could do it elsewhere on the calculator. I don't have to do it on the graph. You can do it on the home screen. So let's try it. Maths, there it is down there, number 9. And it's between 0 and 3. And I want to do 2 times that function, whatever that function is. And it was plus 1 dx. So the answer is 27. In fact, no matter what function I put in there, it's still going to equal 27, provided the original area was 12. You'll need to verify that by hand, but what I've done is shown you that the calculator is capable of finding this solution. You just have to be a bit clever with how you set up your y1, as in your function, choosing it so that it actually works. So that's all we've got time for today. I'm glad you could all stick around. We're out of time, and hopefully you'll download the revision questions as well.